Obrigado por la presentación, pero como notaréis, tengo un fuerte acento español, así que voy a dar la charla en inglés, porque para evitar sobre todo confusiones con palabras españolas que pueden ser parecidas a palabras portuguesas, pero significan exactamente lo contrario, mejor nos ceñimos al inglés y así mantenemos la objetividad científica. Well, I have given the name to my talk of a talk into movement. Sounds a little bit musical, because Professor Pereira asked me to give you some kind of insight about how I see electrochemistry and things like that. So I will very briefly talk a little bit about that. Obviously, this will be a personal view, so completely subjective, and probably many of you would not agree, but it's what happens with personal opinions. And then I will get into the objective scientific part, and I will talk about some of the work I have been doing in the last years, and I'm starting to continue doing in Aberdeen about non-covalent interaction at the electrical level layer. And starting with the first part, electrochemistry is, from my point of view, a very remarkable science. Because, well, obviously, probably one of the things that is more related with chemistry is the conversion of energy, because what you do actually in electrochemistry is you study how you convert electrical energy into chemical energy, or the other way around, how you convert chemical energy into electrical energy. So obviously, it involves the transfer of electrons, and these transfers occurs in an heterogeneous place. It always happens at the interface between two phases. So obviously, the most important thing in electrochemistry is this event, the transfer of an electron, and it happens in a very defined region of space, which is the electrical double layer. So obviously, this means that if you want to do electrochemistry, you have to understand this. You have to understand the interface, and you have to understand electron transfer, because without electron transfer and interface, there is no electrochemistry at all. You just have, well, you can have, at most, you can have normal homogeneous chemistry. But, well, then this is by nature an interfacial science. So obviously, the interesting thing of electrochemistry is always at the interface, from my point of view, or the most interesting part of electrochemistry. I like to paraphrase Karl von Clausewitz, who is probably the first Western philosopher of war. So Oriental cultures have been doing philosophy of war since very early, since nearly the beginning of the Christian era. But in Europe, we were much more, let's say, behind them in this sense, or if you want, we were a little bit more peaceful. And the first philosopher of war, was Clausewitz. And he said this sentence here, if I translate it into English, means that war is just the continuation of diplomacy by other means. And we could say that electrochemistry is actually a continuation of chemistry by other means. Sometimes I think that it's the other way around, that chemistry is the continuation of electrochemistry by other means, or if you prefer, we could say that chemistry is simply a branch of electrochemistry. But, well, most people who simply do chemistry wouldn't like that. But if you think of it, all chemistry involves either protons transfer or electron transfer, or both things. So all chemical reactions are either a transfer of a proton, or a transfer of an electron, or both things together. And this is also the essence of electrochemistry. The only difference is that in electrochemistry, you separate these events into two parts, while in chemistry, they always happen together in both directions. So, well, electrochemistry is also a very old branch of chemistry, probably one of the oldest ones. We can trace it back to the invention of the Volta pile by Volta. And this is what I talked to you about, the interface between what we call an electrode and an electrolyte is the essential part of any electrochemical system. It's the part where the seminal event of electrochemistry happens, which is the electron transfer. And obviously, as I said, conversion of energy is closely related with electrochemistry. And when we want to convert, when we convert energy, or when we do energy conversion, is to have as much power as possible. So we don't just want to have a lot of energy stored. We want to be able to release it very fast. So you can think of it if you have a car. You can have a car with 2,000 liters of gasoline in your deposit, but if you can't use the energy stored in that gasoline in a fast way, so if you release it in a very short time, then you will have power and you will have a Ferrari that drives very fast. But if you can't release that energy stored in gasoline very fast, you will move your car from here to there, but you will need ages. That's power. So this means that power is very closely related with the rate at which reactions happen. So if you want to have an energy conversion system with a lot of power, you want a system which can make reactions fast. And this means catalysis. And in the case of electrochemistry, electrocatalysis. So that's why you will see that most of the work that is, or a lot of work that is done in electrochemistry is dealing with electrocatalysis, because all of us are very concerned with having energy. So we wouldn't have light, or we wouldn't be listening this presentation without energy. And then we want means of converting energy and getting a lot of power. And then if we want to do it electrochemically, which is a very good way of doing it because it's very efficient, then we need to drive electrochemical reactions fast, and we come to a very active field of research, which is electrocatalysis, and which is partly related with what I will talk to you later. But now, after this very short, or maybe not so short, introduction, okay, so how do I see electrochemistry? In addition to all these things that I have been talking about, I do think that there is another reason why I think that electrochemistry is a very remarkable science, and it is because what people have been able to do between the beginning of electrochemistry and, let's say, the 80s of last century, with only measuring two things, which were potential and current. So electrochemistry was, for nearly 100 years, until, let's say, the 1980s in the last century, science in which you only had two things to learn about your systems, and these two things were current and potential, and you had nothing else. And it's really incredible how the people doing electrochemistry until this time, how creative they were, how many powerful techniques they developed to get an incredible large amount of information about the systems. So I really deeply admire all these, let's say, our predecessors who were working with tools which were very primitive and which essentially rested on only two parameters to learn a lot about our systems. I think that there is no other example in science of such a situation. If wherever you look, people has had at their disposal a wealth of techniques, spectroscopic, structural diffraction, whatever you look in science. And probably electrochemistry is unique in that sense. But obviously, there is a limitation. No matter how creative you are, there is a limitation to what you can do if you only have two things to measure. So there are a lot of electrochemical techniques which are very powerful and very important. They give very detailed and very precise quantitative information. And I think that being quantitative in science, and particularly in physical chemistry, is very important. So probably that's what makes the difference between science and something else. Science is quantitative, because that's how you can prove things or disprove hypotheses, being quantitative. And all these techniques were very quantitative. But the good thing that we have is that since the 1980s, we have also had the chance to use non-electrochemical techniques ex situ. They were available very early, but the problem is that they are ex situ. You take your interface, you take your surface out of the interface, and you don't know what happens when you do that. But we also have now a lot of in situ spectroscopies. And we also can work with single crystal electrodes. I don't think that working with single crystal electrodes must be absolutely necessary. It depends on what you want to know. But of course, it gives you a lot of insight on what's the structure effect and what are fundamental things that then you can use and translate to not so fundamental problems or more applications-oriented problems. So now, in the 21st century, compared to the situation that we had until, let's say, the 1980s, we have a lot of electrochemical and non-electrochemical techniques available. We also have the possibility to work with single crystal electrodes. And with this, we can learn a lot. We can get a very detailed information at the atomic and molecular level on the composition and the structure of our interface. And we can study reaction intermediates. We can study reactivity-structure relationship. We can study interactions between surface and intermediates. And we can use all this information to improve and design processes and materials. And that's probably one of the reasons why there has been a huge advance in the development of electrochemical devices in the last, let's say, 40 years. Because we have moved from working mainly on intuition and just trying to increase this and this, but just because you had the feeling that it would work, to have real knowledge on what's going on at the interface and try to apply that knowledge to design things. So now a lot of electrochemical devices and based on real knowledge obtained from fundamental studies that can be translated into applications. So this is a short, I would say, a storyboard on how I see what has been the evolution of chemistry in the last 40 years, 30 years. And I think the 80s were a turning point. In the 80s, two things happened. The development by Clavelier of methods to work with single crystal electrodes, and this was very important too. For the first time, it was possible to make vibrational spectroscopy of your interface. This means that you had, for the first time, chemical information on your interface. You knew what was the chemical nature of the species there. And you could also get information on how they were bonded to your electrode. And you could also get information about interactions between them and about their molecular structure. And a second turning point was the 90s. In the 90s, we had something very important, STM. STM gave us, for the first time, the possibility to see the atoms on our surface in situ, while things were working. And this is something which I think probably people maybe in the 50s could not even dream of. I have been working with STM now for 15 years, and I am still amazed that we can see atoms. So it's something that it means, when I was a student like you are here now, I thought that's something impossible, that you can see an atom. And now we are seeing atoms on a daily basis nearly. And I want also to mention Osawa, who made an improvement of infrared spectroscopy and developed this method, who gives you a huge sensitivity. And the other important thing of this method developed by Osawa is that it increases a lot the time resolution. And I think that the time resolution is the next challenge that we have in electrochemistry. We can do all these things here that I have put in black. And we have learned a lot about that during the last 20 years, maybe 30. But dynamics at the electrochemical interfaces is a real challenge. So dynamics means everything that is moving. It means reaction mechanisms. We don't know anything about reaction mechanisms. We don't know how bonds are broken and formed during electrochemical reactions, which involve something else than just an electron transfer. So there are very simple electrochemical reactions like taking, I don't know, let's say silver plus and making a silver atom. This is very simple. Nothing happens, just an electron transfer. But there are many other reactions in which you take methanol and you get CO2. And there you have to break 4 hydrogen-carbon atoms and form 1 carbon-oxygen atom in addition to the one that you already have. And this involves a lot of things, and we don't know how it happens. And this involves also dynamics. This involves knowing what the reaction steps, what are the intermediates. But it's not only that. All these surface reactions involve species which adsorb on the surface. And if you have one species adsorb on the surface here and another one here, they are not going to interact. They have to come close to each other somehow. And this means moving along the surface. And this is also dynamics. And all these, we don't know anything about that. It's a real challenge because electrochemical systems by themselves have a limitation on how fast you can see things because you have to charge them. And they have what we call a time constant, and this limits the time with which you can work, the time period in which you can get information. So this is a real challenge, and I think this is the next frontier in electrochemistry, and probably will remain so for many years. So this is not bad news. This is good news because this gives us a lot of work to do and something to apply for projects and so on.